Welcome to Spring LIB.
For this problem, on the topic of electromagnetic induction, we are told that a long straight solenoid with a given cross-sectional area and number of turns starts at t is equal to 0 with the current increasing according to a function of time, which is given. Now we have a secondary winding of 5 turns which encircles the solenoid at its center. And the second winding has the same cross-sectional area as the solenoid. We want to find the magnitude of the EMF induced in the second winding at the instant the current in the first is 3.2 amperes. Now, to solve this problem, we know that the changing current in the solenoid will cause a changing magnetic field and hence changing flux through the second winding. This changing flux will induce an EMF in the secondary coil. Now, the magnetic field of the solenoid B, we know, is equal to mu naught times N times I, where mu naught is a constant, N is the number of turns per unit length, and I is the current. And the induced EMF is epsilon, and this is equal to the number of turns N multiplied by the magnitude of d phi dt, the rate of change of magnetic flux. So we first need to find the magnetic field strength. So B is equal to mu naught times N times I. And this is 4 pi times 10 to the minus 7. And that's in SI units of Tesla meter per ampere times the number of turns per unit length, which is 90 times 10 to the power 2, or 900. And that's per meter. And the current is given by the expression 0.16 amperes per square second times t squared. So if we simplify this, we get the magnetic field B to be 1.81 times 10 to the minus 3 Teslas per square second times the time t squared. So we have the magnetic field as a function of time. Now the total flux through the second winding, so phi 1, 2 is equal to, and this is the magnetic flux, 5 times the magnetic field strength B times 2 times 10 to the minus 4 square meters. So if we substitute B into this expression, we get the flux through the second winding to be 1.81 times 10 to the minus 6. And this is Webers per square second times t squared. So now we have the field as well as the flux. The magnetic flux is simply the field multiplied by the area. And we have both of these in terms of t, or as functions of t. So now we can calculate the induced EMF. Now we know the induced EMF, epsilon, is equal to the total number of turns N times the rate at which the magnetic flux is changing, d phi dt. And so this is simply 3.619 times 10 to the minus 6, and that's volts per second times t. So we take the time derivative of the expression for the flux that we have above, and we have an expression for the EMF. Now, we are told that the current is 3.2 amperes, and we need to calculate the EMF at that time. So we have 3.2 amperes equal to 0.16 0.16 amps per square second times t squared. And we go back to this expression so that we can find t. So rearranging, we get the time when the current is 3.2 amperes to be 4.472 seconds. Now that we have the time, we can put this back in our expression for the EMF, and we get the induced EMF in the second winding, epsilon, to be 3.619 times 10 to the minus 6 volts per second times t, which is 4.472 seconds. Hence, we get the induced EMF in the second winding to be 1.62 times 10 to the minus 5 volts.